Yeah, it's one person. Sound. Reactions that we're going to talk about will be the uh, metal mediated reactions like the Tokai reactions, uh, and then also how to convert alkynes or triple bonds into alkenes using boranes and other reagents like that. So for the metal mediated or the metal catalyzed olefination, we're going to talk about the Tokai reaction. And that's using basically using like a chromium species. So you use a chromium species to actually convert an aldehyde into a uh, alkene, right? So there's a couple of ways to do this, and this is basically your aldehyde here, and you can treat it with a uh, trihalo alkene like this, and chromium dichloride. Or you can treat it with, you can extend that chain and add a group to a dihalo alkane. And this is when this technology first emerged, you couldn't do that, right? You actually could not add more than one carbon onto that alkene, right? You can only add one carbon. And like if you look at the, let me take this down a little bit so I can make some room. Right, if you look at the initial reaction on the right, right, you're able to get, let me number that, R1. You're able to get this trans alkene. Right? So like a trans halo alkene, which is that's a good thing because those halo alkenes are great precursors for vinyl lithiums, vinyl iodide. I'm sorry, vinyl lithiums, and then you can even convert it into other organometallic species, or you can use them in like organometallic coupling reactions, which we're going to talk about a little bit later. So that's the product from that reaction where and this carbon right here is the carbon that was here, right? And then if you look at the other reaction where you've extended the chain by adding another R group, and you still get the E isomer as the main product, but now you've extended, right, the chain. And so it just depends on what your goal is. And the R2 on that diiodo alkane can be alkyl. It can be an alkyl group. It can be a arrow group, right? It can be a borane, which is good because these alkenes can be precursors to other reactions, right? Other types of reactions, and a boranes are uh, precursors for like Suzuki coupling or other types of coupling reactions, right? It can be a silicon, right? Or it can even be a tin species, right? And the reason that's important is because again, that alkene that's synthesized through this method, you can take that alkene and that may be a bridge between two pieces in a larger molecule where you pull those two pieces together and cyclize some large natural product or something like that. So having this type of scope where R2 can be you know, a boron or a silicon or a tin is very, very important. All right. So how this works, let me show you that. And then we're going to look at some examples of the applications. And if you don't get all of this stuff down, don't panic, because uh, I'll have this. I think this is already uploaded, but I'll have this package uploaded to Blackboard in the course documents section. All right. So you take your your alkane, and then you add to that 2 equivalents of chromium dichloride. Right. So now that CH group, is here, right? It does an oxidative addition into chromium. Well, chromium does oxidative addition into uh, that carbon. Right. And so this is your reactive species right here that will attack your aldehyde. So it's this plus whatever my aldehyde is, right? And once you attack the aldehyde, you generate this intermediate that looks like this. So this is your aldehyde right here. And now you make this oxygen chromium bond here. So this is still chromium 3. Right. And so now the chromium can now eliminate. So you just do an elimination here, boom, and then here. Right. And so from that elimination, right, so the first step is going to be like an oxidative addition. And then the last step is an elimination. So obviously you're going to be able to, from that elimination, you can get 2 alkenes, but you can see from the stereochemistry here that R1 and X are going to be on opposite sides, right? Because if you look here, the X is actually on a wedge line, and then R1, on the other side where R1 is, it's the hydrogen that's on the wedge. Let me fix that. That's sloppy. Right? So you can see from that intermediate that R1 and X are going to be on opposite sides. So your major product is going to be here. And then the minor product is going to be the cis product. Like that, right? So as far as the mechanism is concerned, it's a fairly straightforward mechanism. The first step is oxidative addition, and then you do that twice. So chromium is going to do oxidative addition twice into that carbon because there's multiple halogens on there. And the way that oxidative addition works, let me just give you a little Side note on that. If I can get this stupid pen to act right. I'm jealous of Dr. Reeves. She's like the stylish guru. I've never seen her have a problem writing on her screen. Right. So oxidative addition, you have like some uh, carbon has to have some type of leaving group or electronegative electron withdrawing group on it. So we'll say that this is CX. X can be whatever halogen or triflate or some other leaving group plus a metal. And then what happens is this complexes, right? So you have your metal here, and then you have a complex between that CX bond and the metal. So it's oxidative addition because here the metal is going to boom attack here, and then you use the electrons in the bond here to attack the metal. So you end up with a complex that looks like this. And in the process, the metal gets oxidized. Right. And in order that the reverse of that is what we call reductive elimination. So you have oxidative addition where you add to the metal across the carbon halogen or the carbon electron withdrawing group bond. And then reductive elimination is the opposite of that, right? So you take a pair of electrons and go here, and then you give a pair of electrons back to the metal. So you can end up reforming CX plus M, right? And so most of the times, if you have a metal catalyst that's going to go through a catalytic cycle and be used for a particular reaction, normally this is how it works. It goes through some type of oxidative addition step. And then at the end of the cycle, it goes through some type of reductive elimination step in order to give you what your product is. So normally, like the metal, you'll do some other type of transformation where you do your oxidative addition, then you bring in another piece to add to the metal, and then the two separate pieces end up together in the product. So we're going to talk more about those types of coupling reactions a little bit later on in the class. But anyway, so for the Tokai reaction, uh, it depends on. So these are just some trends for this reaction. Right. So for that, for your alkyl halide, the rate of reaction is iodine is greater than bromine, which is greater than chlorine. And there's a reason for that, right? Though the larger the halogen is, the further away it is from the carbon nucleus. So it makes it easier to do oxidative addition into a bond between carbon and iodine than between bromine or chlorine. Not to say that they're that much slower, but the carbon iodine bond is the weakest out of all of those bonds. Uh, if you want to control the stereochemistry, right, the way to control that is to use an alkyl chloride. So you get more stereo control with chlorine as your halogen than you do with a bromine or iodide. You can do aldehydes or ketones, but aldehydes are faster. Right? So an aldehyde is going to, for obvious reasons, is going to react faster because it's a lot less sterically encumbered than a ketone. Uh, and if you have a what's called a 1,1 geminal dihalide, where you have something like this, That's going to give you the E isomer as the predominant isomer. All right. So for this particular reaction, let's look at a couple of examples with this Tokai chemistry, and then we'll look at another metal mediated process. Because I think there's a I don't know if the TEBI is discussed in here or not. The TEBI and the instant TEBI, that's fine. But let's look at some examples. So for this aldehyde, right? If we just take the trihalide, and chromium dichloride as my metal, and do this in THF, right? I'm going to abbreviate the product so I don't have to draw that chain out. But I'll just abbreviate it here. The product and the ratios, right, are as follows. So if I have, let me move this up. So if I use chlorine as my halogen on my alkyl halide, iodide, or bromine, right? And in 2 hours or between 1 and 2 hours reaction time. So I get a 95:5 E to Z ratio, right? With chlorine as the halogen. I have I get a 83:17. You can see the ratio is starting to drop off some with iodine. 83:17 E to Z ratio with iodine. And then with bromine, I get a 95:5 ratio also. Right. And so when you think about that, there's something to be said for rate and selectivity. So usually if the rate is faster, like if it's a higher rate reaction, then it's going to be less selective. And so that's probably why you see, if it's a lot faster. So that's probably why you see the drop off with the iodine, because again, we said that that's the most reactive of your alkyl halides, right? There's another issue with this reaction, and this is why it's called a metal mediated reaction and not a metal catalyzed reaction. There with your chromium, right? There's a big difference in something being catalyzed and being mediated. This is actually excess metal, so you actually need 6 equivalents of metal, right? So that's a 6 to, and then you need 2 equivalents of your alkyl halides. So it's basically a 3-to-1 ratio of metal to alkyl halide, right? And then 1 equivalent of your aldehyde. So this is not it's not catalytic, right? And that's very important to understand that. Right, it's not a catalytic reaction. A catalytic reaction will be anything less than 1 equivalent, even if it's 0.9, right? It's still catalytic. But the ideal situation for a metal catalyzed reaction would be somewhere between 1 and 2% catalyst or less, right? So anytime you see the metal in a 1-to-1 ratio, or the promoter in a 1-to-1 ratio, then it's not a catalytic reaction, right? So you get a lot of side products, and you get a lot of stuff that's generated in stoichiometric amounts that you have to get rid of after this reaction, right? But going back to the rate, um, again, you can see the iodide we said was the best, the most reactive out of all of your alkyl halides, and so this drop off in selectivity is probably due to the fact that as you increase the rate, sometimes you decrease selectivity. So increased reaction rate can sometimes come with a drop off in selectivity. All right. All right. So there's also an example here that we can look at real quick to show the selectivity as it relates to ketones versus aldehydes, right? So if we have this example, and I'll show you here. So I have an aldehyde on this end and a ketone on the other end, and it's the same as it's chromium dichloride, and then this is done at low temperature in THF. Right. So for the aldehyde reactivity, you get the vinyl iodide, the E vinyl iodide at that, in a 81 to 19 selectivity, and that's E to Z. And what you don't get is the ketone. So I'm gonna show this. I'll just show this like this. The ketone stays intact, right? And then you get a little bit of this product. I'm just gonna abbreviate that. So you get a little bit of this product where both the aldehyde and the ketone react, but you only get that 5% of that. All right. So the selectivity, as far as like what type of carbonyl you use, is pretty selective for aldehydes over ketones. You get this in 75% yield. Then you only get 5% of the uh, species where both the aldehyde and the ketone react, and you don't get any of it where it's ketone over aldehyde. Let me show you another example, and that's here. This is from Okazo. This is 1987. Jax. Page 951. All right, so this is my aldehyde that I'm starting out with, and this is again the geminal dihalide. So where you've extended the chain past one carbon, and normally if it's under previous conditions, if you extended the chain, then you ended up with like some uh, beta hydride elimination and some other like side products that were undesirable. So but for this particular reaction, you have right. This is my dihalide, and I'm doing this again with chromium dichloride and I get out this alkene, all right, 97% yield, and then a 94-6 E to Z ratio. All right, so that's excellent. And the other part of this that makes this, when you compare it to like the Vidig or compare it to like the Horner Emmons or Clark Steel, is that the functionality now is like you don't have any other functionality to deal with, right? So if you just wanted to install a trans alkene and high yield and high selectivity, this is a great method to do so. You don't have to worry about additional functional groups that come along with using something like the Horner Emmons or uh, the Julia coupling or something like that. If you just wanted to add in a alkene, this is a great method to do it. All right, anybody got any questions about anything? All right, so even to show the utility even further, you can actually, this method has actually been applied to different natural product syntheses. I'm going to pick one of these out, and this is from, this is Williams. And this is 1998. And JOC, page 2982. Right? No, I'm sorry. I was looking at the wrong reference. It's in Jax. It is 98, and the page number is 11198. Right. So here again, this is this is used in the synthesis of this natural product, amphedenolide J, and I'll show you what that looks like. And so let me show you the reaction first. So that's that, and then again, anytime you're doing a synthesis, a total synthesis, you're always going to see these protecting groups, right? Always going to see these protecting groups because, again, you want to keep those functional groups from reacting with things that they don't have any business reacting with. That's the best way I can put that. So that's that. And again, you see another alcohol protecting group with a THP group on it. And if you remember when we talked about those protecting groups, it's always strategic, right? You use different protecting groups based on which alcohol you want to deprotect first or last, right? And so for this particular species, you're going to treat it first with DMP, oxidize that alcohol up to carbonyl, an aldehyde, and then you want to treat it with chromium dichloride and then triiodomethane, so CH3, and you're doing this at room temperature, basically 23 degrees Celsius, and you get the product in 77% yield, and your E to Z ratio is 19-1. Which is excellent. right? So the reaction takes place here. So I'm just going to abbreviate that part. Right, and you get that trans iodine. And again, this is important because that vinyl iodide is a great precursor to many different reactions, right? That's a doorway into uh, coupling reactions. It's a doorway into, you can convert it into an organometallic and use it as a nucleophile. So it just depends on what you want to do. But the product, the final natural product, let me show you what that looks like. And then you can see where that cyclized, where it was used to cyclize. So, right, so this is where the alkene is, and then it actually cyclized with another fragment, probably intramolecularly, and also added in this fragment here. Right, so you can see right away the value of having a method like this. And to have it be so facile and be done at such under such mild conditions is excellent. So this is the natural product that they eventually synthesized. And you can see immediately right here, this is where that vinyl iodide came into play and cyclizing that natural product, right? So again, if you can make these vinyl iodides, vinyl bromides, vinyl chlorides, they are great precursors to many, many different reactions, especially coupling reactions. It looks like this was some type of nucleophilic addition based on the alcohol here, right? So probably the precursor to, and I don't have the paper to pull it up, but probably the precursor to this final structure. This alcohol may have potentially been an aldehyde, something like this, just kind of hanging out. And then that vinyl iodide converted into like a vinyl lithium or a vinyl granular, and then used to attack that aldehyde. All right. All right. Any questions about anything? Uh-oh, what happened? I don't know what. My technology is failing me today. All right. So what I'm going to do, I'll take this information. I'll put there's a big packet that this comes from. I'll make sure that you can see that in Blackboard. And then on Monday, we'll talk about olefinations from triple bonds. And then after that, we're going to move to a new section and talk about conformational analysis. And then we'll just keep rolling from there. If you look at the syllabus, you'll see the conformational analysis section. We actually skipped it because it was supposed to come after MO theory. So we'll start that hopefully on Wednesday. And then after that, we'll go down to the section where it says asymmetric catalysis on your syllabus. All right. Any questions about anything?
As long as all of this is posted, we're good.
Yeah, I'm gonna post it, man. It's already. If you look in Blackboard, let me stop recording. Now I don't need to hear all our conversation.